over by now quite large area, and I found it somehow very difficult. It's not the first time I'm giving you this, so I took some old slides and combined them, but then you are not happy. And so two things are, I think, help a lot. First, that Guy Nason is giving another overview talk over a very related subject this afternoon, also locally stationary process, and I think the two talks will complement each other in a very nice way. And the second thing, I was in a cafe this morning and I wrote to the last slide, and then I had the idea, wow, I should have presented this in a completely different way. And I will stop in the middle and do a little bit on the blackboard, and I think this will be the most important part of the talk somehow, because then you will really get some overview and understand a little bit what is going on in this area. So let us look at this non-stationary process. So this is an AR2 process. You all know that one. And the innovations are, for example, Gaussian with variance 1. So the variance is, so the standard deviation is here in front. And now the whole thing is time varying. And you all know that this process has two roots, and these are the coefficients. Looks fairly complicated, and these are the roots. And if you, I think you all know that this root is close to the unit circle, so we have, and it has it is a complex root with its complex conjugate. So basically you have a fluctuation, a periodic type of behavior, and so this is time varying. This is the process. So you have so you see here the fluctuation, and you see that it's here, it has a short period length, and here it's a longer period length. So you see here the long cycles, and then you have short cycles and long cycles. And so basically this is constant here, this is constant, and this is here basically the parameter curve A1, which is fluctuating. And so this is one example. Here is another one, the same process, now with different specifications. Now this one and this one stay constant, and this one is fluctuating. So basically, if you, in particular, if you have simulated these such processes, it means that it's kind of an envelope. The sigma is kind of an envelope of the whole process. So when you take the same specifications of coefficients, the same innovations, and when you double the sigma, the whole thing, this follows from the moving average representation, the whole thing will just be blown up, right? And so this is like an envelope. These coefficients are constant, and here we have a specific sigma, and you can see what the sigma is. So sigma is here, this curve, and this is a frequently used model for example, for explosions. So basically you have here, or for earthquakes and explosions. So basically if you have an earthquake, it quickly starts, and then here's this is the point, the mode, here the mode of the curve, and then you have these earthquake type of behavior. So these are two examples of non-stationary processes, such that you get an idea what I'm talking about. Now, the point is, what is the question, for example, at this point? Well, first we want to estimate these curves here, and then once we have, so to estimate the curves is not that difficult. I mean, you would all have quickly an idea if you would be sitting for 10 minutes or 1 hour, and you would quickly come up with an estimator. So basically local least squares is something you fix some, basically you fix some interval here, and say you fix the interval here, and then you do a local least squares estimator, and then you have these you have an estimator for these parameters here, basically at this point. So you assign your estimator to the middle, then you shift the segment, you make again least squares, you assign the estimator to the middle, and so you move on, and so by that way you get three curves which are estimators for this thing here. Okay, this is a very straightforward idea. You do not need lots of theory for doing that. Then the next step comes. Two questions arise at that point. First, you want to plot a confidence interval around the curves. How do you get the confidence interval? Okay. Because first, it's very difficult. I mean, these things are getting very difficult to derive it exactly. Of course, you can do a bootstrap or something like that. But really, to get a confidence interval is not that easy. And typically, if it's not that easy, what do? You prove a central limit theorem and take the asymptotic confidence interval, or the confidence interval coming from the asymptotic distribution. So the first question is, how do we prove a central limit theorem for our estimators? So we have estimators, how do we prove a central limit theorem? This means asymptotic statistics, and asymptotic statistics would mean in this case, well, we have two choices. The first one is to do asymptotics just to move on. So basically, we extend this here forever, but this doesn't tell us anything about the behavior at the peak, right? And the next one, the alternative is the idea coming from non-parametric statistics, where we say our object of interest is this curve here. Our object of interest is this curve here, and we want to estimate this curve. By the way, these dark things is one estimator. So our object is this curve, and in our asymptotics, this object of interest should stay fixed. And then we somehow sample in a more denser way from the curve. This is non-parametric statistics. So basically, non-parametric statistics, in its simplest form, is you have some curve, and you have your observations here, which are kind of disturbed by noise, and then you assume that basically in your asymptotics you sample the curve more densely, and this is the way you do asymptotics. And we do it in the same way. We basically assume that we sample from this curve, from our parameter curve, more densely, and this gives us a rescaled setting where we basically can do our asymptotics. The whole thing gets more difficult in this time series context because we are ending up with a triangular array of observations. And this is what people familiar with time series do not like at the beginning. So somehow it's the way the infill asymptotics comes in. We sample somehow more densely from the curve, and this gives us more and more observation at each time point. So basically, we fill in artificially observations, and the goal is really to prove a central limit theorem, say, afterwards. And then we have our asymptotic distribution, and then we can use it for a confidence interval. This is the goal. It's not really to describe the process in a nice way or whatsoever. Okay? The second question is, and this is also answered by the same approach, the second question is, okay, I've suggested an estimator, and then someone of you says, hi, what about local polynomial fits? Can we do local polynomial fits? Yes, we can do. And then we can calculate it, and we have another estimator. And then the question is, which one is the better estimator? And in order to answer it, you need asymptotic theory, typically, not necessarily, of course. And so this question, if we have two estimators which are competing, can be answered again by this infill asymptotic approach. Now, so somehow this is now I summarize this. So basically, the rough idea is that a locally stationary process is close to a stationary one on every segment. But this is only the rough idea. And to be more precise, more rigorously, and this is the narrow idea which I just told you, local stationarity is an infill asymptotic approach, rescaling of time of the parameter curves. So we rescale the parameter curves, fill in artificially more data as in non-parametric statistics over there for the investigation of non-stationary processes. So it's not a subclass of non-stationary processes. It's somehow in the mathematical sense or in the sense I'm advocating it here in this talk, it's more a way to build the bridge between non-stationary processes and mathematics and investigations, which are necessary, for example, if you want to construct a confidence interval. Now, example, you saw that we have this AR1 and we want to rescale this parameter curve. Similar to non-parametric statistics, here parameter curve stays fixed. And this is the point I already indicated. This leads to a framework for the use of asymptotic concepts such as asymptotic normality, efficiency, LAN theory, rate of conversions, adaptivity, and so on. So basically you have all these tricks and playgrounds from theoretical statistics or from statistics, and you can apply it and discuss it in that framework. Very important to say, without infill asymptotics, processes with time-varying parameters have been investigated by several authors before, notably by Morris Priestley and by many others, and there are still many papers without these infill asymptotics. And to make a very clear statement, these are very smart people. These have been very smart people, and these still are very smart people. Many of them are very smart, doing very decent research. And it's not, I'm not saying, wow, well, this is not a good research. You have to apply the idea of rescaling, otherwise you cannot publish your paper or whatsoever. I mean, this is ridiculous. One really should keep in mind there are many people working just on non-stationary processes from a different viewpoint. They do not apply this rescaling type. They are not that much in mathematical statistics, but they are very, very smart ideas in those papers. So it's not that I'm saying this is the world of local stationarity, this is a different world. So it's really a mixture of ideas and back and forth and whatsoever. I would also say, on the contrary, it's not that these people working on locally stationary processes do not have ideas and they only do the mathematics. I mean, this is also something I would like to say, because when you look at it from a mathematical angle, you really create lots of ideas what you can do and how you can improve things, and so it's really I think a back and forth between these worlds. So let us go. Perhaps, I don't know, I skip that one. Time is running fast. Let me skip that one completely. Perhaps I get back to it later on. Here is an idea on the benefit of rescaling. A toy example, time-varying AR1. Perhaps I already convinced you, but here is a more complicated one. So we have a time-varying AR1, so the simplest model I can have. And then we can easily cook up, say, our Yule-Walker estimate of a segment of length, which is equivalent to least squares. So basically, our estimate is the covariance of leg 1 divided by the covariance of leg 0. And now we calculate the covariance a little bit different, namely, we take our product xt plus k, and weight it with the kernel. So basically, the kernel centers it at a certain point, and then it basically is smooth towards the edges. You can basically, it's very close to a tapered estimator. Basically, you can put weights here and put weights there, and it's very similar. Now, first result, I already mentioned that it's asymptotic normality. You get a confidence interval for that. Second result, we can conclude by mathematical calculations that the tapered covariance estimator, this is what I just explained to you, is equivalent, and also local least squares is equivalent. Again, this is a mathematical result. You would expect it without these infill asymptotics, because you can look and it looks similar, and then you can see this thing get smaller. So, but when you really want to bring it to the point, you have to really do some mathematics, and this would mean rescaling at that point. Now, the question is, what is the mean square error? Can we find the optimal bandwidth, the optimal segment length? So basically, this is on a segment. How large should the segment be? This has been answered, I don't know, 100, perhaps even 1,000 times in non-parametric statistics. And what we can do it here, we can calculate within this infill asymptotic approach the mean square error. It has the same structure, nearly the same structure. It is the bias term squared, so it's the bandwidth squared. We have, this is the second derivative of the curve squared. We have some constant coming from the kernel. We have 1 over the effective sample size, again a constant from the kernel, and the asymptotic variance. And so there is one important difference. This is not the original curve. Unfortunately, it's not. It's this A tilde is not the curve A. It's related to the curve A. So for the moment, you should think of it as being the curve. Now you can play the game. I mean, this is high school calculus. Take derivative with respect to B, and you get the optimal bandwidth out of it. This is the optimal bandwidth. You get this nice this expression, also similar to non-parametric statistics. If you multiply it by n, you have the segment length in normal time. And you can also, and this is more challenging, but it has been solved by other people before, you can minimize this with respect to the kernel, and then you end up with this optimal kernel, which is the Epanechnikov kernel. Two things come up here if you look at it more carefully. The first one is the question of adaptive bandwidth selection. This is the optimal bandwidth provided that you know the curve, right? And which you do not. So you can do a multi-step procedure where you plug in and so on. This has been done, and you can do it here as well. And or you can cook up other methods, but this has not been investigated properly. There are some approaches, so this is an open research question, by the way. The other thing is this n to 4/5. This is very disturbing, because the question arises: can we translate it back to the non-rescaled world? Right? I mean, we have our starting problem, which is not infill asymptotics at all. It's not rescaled, nothing. I mean, we have just our data. We go artificially to the infill asymptotics, to the rescaled world. We get this nice result, but then we want to translate it back. What is the optimal segment length? And it depends to n to the 4/5. And the point is, I mean, you have your process here, say, it goes like that. And I mean, if you want to determine something locally here, I mean, it doesn't matter how long the stretch is at all. So basically, it should be completely independent of n, right? And luckily, there is a way out, but it's more complicated than in the asymptotic normality result. And this is the following. Here's the expression. And the question: how would you estimate the second derivative? Well, in a very naive estimator, I don't say that it's a good one. I don't recommend this. But a naive estimator would be the second difference for the second derivative would be the second difference for this curve divided by the step size. Now, this basically is fixed. This is the curve in the rescaled and in the non-rescaled world, so whatsoever. But then here you divide by 1 over n squared. And when you plug this in here, I mean, it means an n squared here, an n squared. You squared the n squared again, means n4, n to the 4/5, and it drops out. Luckily. So, otherwise, basically, we could throw away this approach, right? So it's what I want to say with this example is that you to those who are not familiar with the approach is that it really makes sense. You can derive results with this approach and translate them back to your really data at hand. And to those who are working with that, maybe to think about carefully at all stages, can you really translate it back? And the answer should, of course, be always a yes. Now, so here is the next result: optimal segment length data adaptive solution. Here are other to tell you a little bit on estimation procedures. I could do this overview talk with long lists. I mean, 10 estimates, 10 methods, 8 bootstraps, 10, well, whatsoever. This is all very impressive research, but the idea. So I do it here once for the estimators. So how can you do that? So the first one is the simple one, which works always. So basically, if you're a locally stationary process, you can always apply a stationary method on a segment. Whatever it is, it could be a test, it could be some principal components, whatsoever. But it's a simple way of doing it. You should keep it in mind. So basically, we can always take our segment, shift it, and apply some stationary method on a segment. And this is what I did. So basically, it's a stationary method on a segment. Now, basically, we can do a little bit better and apply a local polynomial fit on the segment. So basically, you have your segment. Let's do it a little bit larger. You have your kernel, and then you want to estimate some parameters, say here, and instead of doing a local constant fit, you could do a local linear fit, or even fit a local polynomial to the curve. And so, I mean, if this is the curve, then it would look this way, so your local polynomial, and then you get a better estimator, and you get an estimator in addition for the derivative. And if you apply higher order polynomials here, you can have estimators for the higher order derivatives. Then you can just do a parametric fit, and this is very often good for short series. So very often people say to me, wow, locally stationary process, it's for big data, right? I mean, and it's not for short data length. And because their intuition is somehow right. I mean, you want to look at small segments all the time. I mean, if you have the idea that it's only related with looking at small segments, then you need enough data in your small segments, and then of course you need huge amount of data. But another way is when you, in particular, if you have a short, if you have a short serial length, you would apply, say, you would do a polynomial fit with a few with low order, and then you can really fit nice. It's a nice way to fit curves to really short data series. And I will show you an example on the next slide. Then you could do, for example, expand this curve with respect to some orthogonal basis. Wavelet is a prominent example, and Guy Nason will certainly comment on that in his talk, so I skip it here. And then another way you could say, okay, we define some class which say all monotonic functions. Think of the second example. The sigma was from the mode, from this explosion. It was a monotonically decreasing function, and we can just minimize this problem and fit those curve out of this A curve. There it was the sigma, what we could say, okay, so it doesn't really make sense for the A, but to have all monotonic functions. But we can define this class A as a member of some certain family of functions, and then you are in the non-parametric world, you have covering numbers, you have to make sure that this class is not too large, and then you can do asymptotic statistics for it. Here is an example. Again, this starting example, and here we have fitted a polynomial. So basically, these are 128 data. You can debate whether this is a small or large amount of data. It would also work with 64, perhaps even with smaller sizes. And then you cannot. It's difficult to estimate this non-parametrically. So we took polynomials here and fitted polynomials to the curve and estimated this. And the original curve was this one here. And then we had with the polynomial, this was the fit here. So you get a very decent fit with when you have a small number of data points. Now, I haven't. Let's go back perhaps now to the slide which I skipped. Yeah. So sorry. This is now So now let's look a little bit about stationarity. So stationarity typically means we have the mean, we have the covariance, which just depends on the lag. Then we have the spectral representation of the process, of a stationary process, which is a Kramère representation. This looks pretty scary when you see really the stochastic integral for the first time. It's equivalent to a moving average representation somehow. Right, so you can replace this by a moving average representation. And then we have the spectral density, which is f of lambda, a of lambda squared, the transfer function squared, and which at the same time is these Fourier transform of the covariance function. And we have the inversion formula, where the covariances are the backward transform of the spectrum. And when we now go to, let's skip this one here. Now let's go to local stationarity. We have this, the mean may become rescaled if we look at a mean in addition. The question is very difficult how, when we have a time varying covariance of lag k, which depends on t as well, somehow how to rescale this covariance function. So we skip this for the moment. For the AR case, we already have seen it. We rescale these two curves here. Now the spectral representation, we can rescale. We can retain the Kramère representation when we rescale this transfer function here. Oops. Why does? I'm sorry. Yeah, there it is. Sorry, I pushed it wrong. So when we rescale this function here, and we will take this for the moment as a definition of local stationarity. This looks scary if you see it for the first time, so you can also say we take xtn equal to j equal minus 0 to infinity, say, let's call it b t over n epsilon t minus j. This looks maybe less scary if you are not familiar with this definition. So basically, we take here a general moving average representation and we rescale all the coefficients. And the idea is to have a general class of processes. Now, the spectral density then is this a squared, and then we can use this inversion formula. So basically, it should be the Fourier transform of the covariances here, and we can use this to define this back and then have a definition of that. So basically, we artificially define some covariances, and the scary question is, are these really covariances? And the answer is yes. The so defined covariances are the covariance really of the process up to some very small term. Now let's move to estimation. You saw that. Here is the spectral density, by the way, of this example. So this is the true spectral density. So this is frequency, this is time axis, And if you look at a certain time point, you have one peak, and it means you have a cycling process. You have one peak at one frequency, and then it's going like that. And this is the true one, and this is the estimated one. This looks pretty good, and the trick is not to plot the difference. If I plot the difference, it looks less good than you see the point. So let's leave it for the moment for this talk. It's nice, right? We all agree. It looks pretty nice. Now, let's move to estimates. The first thing is we have this covariance estimator. Again, we are in the stationary world for the moment. So we have our covariance estimator. You all know that one. Then, provided the mean is 0. The spectral density estimator, you all know this as well. The periodogram, you can write it as a Fourier transform of these covariances. It's really exact. We have also, we can retain this inversion formula in the on the estimation side. The Fourier transform of the periodogram is these covariances. By the way, you have to smooth the periodogram. You all know that. And then we have the kernel estimator of the periodogram, say when we need to smooth it, so we make a convolution with the kernel and we get a decent estimator. Now, what is in this local stationarity world? The point is we have to localize this, and this was a very nice idea by Rainer von Sachs and Michael Neumann. They wrote a paper on spectral estimation, and they really did the very radical view. They localized it by just looking at one pair. Wow. And this, of course, is not consistent, and we have to smooth it. So this is really unsmooth, but it's really localized. And in order to do a better job, we move from t k half steps to the left and k half steps to the right. And then the point is we now retain this. We plug this in here, and we have our we make a Fourier transform of this. And this is the pre-periodogram, also from the paper I just mentioned. And the point is now it's quite clear you have to smooth it in time. So basically the smoothing is here missing. So you need some sum over t, some local sum over t with the kernel. And when you plug it here, the local sum over t, you can interchange sums. So basically you can sum this t here. You can average this pre-periodogram over time. And in addition, you still need the smoothing over lambda. You will see it in a second. Inversion formula, let's skip. And here's the estimator I just showed you. So we start with j. We smooth it with the kernel over time, and we smooth it with the kernel over frequency. And this gives an estimator of the spectral density, the time-varying spectral density. Now, perhaps the key property, which is a very nice one, is when you average this pre-periodogram over time, you end up with the ordinary periodogram, which is a very nice feature. So basically it's sliced. You have this pre-periodogram gives you really local estimates at each time point, and if you sum it up, you have the periodogram. Now, this is one really theoretical way of doing things is to look at the empirical spectral process. This is fairly theoretical, and I only want to touch it briefly. But somehow, and I will tell you later why, it's the key of locally stationary processes for quadratic statistics. And so somehow in the traditional stationary world, you can write several statistics as the weighted integral of the periodogram, for example, the covariance. And now we do it, skip that one, we do it here in the locally stationary case. We take this pre-periodogram, which is this strange object, and weight it over time and weight it over frequency, right? And this is an theoretical object at the moment. We are able to prove results for that, in particular a central limit theorem and an exponential inequality, which is the important thing. And then it has many applications for locally stationary processes. And I think it's not really a good overview if I now go, this is A, this means A, this means B, this means C, this means D, and so on. Let's rather look at the general picture, and so I skip this a little bit. But it's basically, let's look at one. If you plug in the exponential here, then we already know we end up with a covariance estimator. And then we have to plug in a kernel in addition in time, first to smooth that thing and to localize it, but this gives us a local covariance estimator. So perhaps you take this one here, this is one example as to understand why it makes sense to look at this. This was the second example you already saw. Your spectral density, you plug in a kernel in time direction and frequency direction, and so on. The important thing, and I will get back to this one, is this one here. It's the gradient of some spectral density, and this is very closely related to the maximum likelihood estimate. I will get back to that. Now, the point is we are able to derive central limit theorems and an exponential inequality and a maximal inequality, so we can have somehow as a corollary a lot of results for many statistics. So it's somehow really a nice tool. A common misunderstanding, and this is the most important slide of the talk. And this came up to me in the cafe this morning. So if you are almost sleeping, it's a good time to wake up again and catch one more slide. Common misunderstanding. This is all about spectral methods. I hear that very often. And the point is, no, it's not. No, it's not. It's not on spectral methods. It's not on spectral methods. And this is a little bit difficult to understand. And if you understand this, you have learned a lot about stationary time series and also about locally stationary time series. Basically, let's do it. I really changed to the blackboard, and I think the point is you really have to view, and I mean this picture holds for all areas of statistics somehow. Basically, you have somehow here the framework in which you are working. Framework, and this means basically it means, for example, the set of assumptions. And somehow, if you do a good job on this very stage, I mean, you really have a rich class of process where you can handle a lot, right? And then you have in the second stage you have the world of techniques. And here I mean mathematical techniques. And examples are, for example, examples are, to understand what I'm talking about, is a central limit theorem, and you have an exponential inequality. Right? And then the next thing which we are all interested on at the very end are models, methods. So basically, statistical methods, let's call it methods, models, and so on. For example, this is a huge world. So basically you can look at an MLE, you can have a confidence interval, you can say let's bootstrap our series, so and so on, right? And now to understand this thing here, the first one is this time-varying Cramér representation, which looked so scary if you do not know about this, or this one here. This falls in category 1. So basically this is really the framework in which we are working, right? This is the framework in which we are working. And now I've lost my, thank you. This is the framework in which we are working. And then there come the techniques. This is the second bubble. The techniques, exponential inequality, central limit theorem, cover the, basically this is the second bubble. And the point is, when people say this is all about spectral methods, then they do not know that basically this covers the general quadratic form of for locally stationary processes. So you can really formulate it in the time domain. And to give you an indication for that is let's write down a Gaussian likelihood. Okay? How does a Gaussian likelihood look? Well, you all know that it's the exponential minus 1/2 x dash sigma to the min x. Okay? This has nothing to do with time series, nothing to do with locally stationary processes. Now, for stationary processes, this sigma is a triplets matrix. What is a triplets matrix? Sigma is basically of this form. This is a triplets matrix. Okay? This means stationarity. This is a triplets matrix. Now, it was really, these were the old guys like Peter Whittle, Grenander, Chege. They discovered that the inverse of the triplets matrix is not a triplets matrix, but it's very close to a triplets matrix. So basically, if you have a stationary process, these people discovered this is approximately of this form. Okay? And this was the huge contribution by Peter Whittle. I have prepared an extra slide for Peter Whittle. Maybe I will not make it. He did it long before his time, and he didn't get any recognition for it at the beginning, but it was a really breakthrough for stationary times. Here's what he did. And he discovered that the inverse is also a triplets matrix, and then he applied triplets matrix theory from Grenander and Chege. And he basically, you use this beautiful theory from Grenander and Chege, and it explores you the whole world of stationary Gaussian stationary likelihood. And it's a difficult word. You prove Lecomte theory, LRN, and so on. It's all triplets theory. Now, this thing here, this statistics, this one here, you can rewrite it as a quadratic form. It's a quadratic form, and it's the general quadratic form in that sense. Basically, now we are in a locally stationary sense, and basically this belongs to a certain time. So basically the time is here in this direction. So basically when you retain the same pattern of triplets matrices and make them gradually changing, so instead of being constant here, these subdiagonals, the subdiagonals are gradually changing, right? These subdiagonals are gradually changing for non-stationary process, for locally stationary process. And this is the quadratic form. You can rewrite this one here as being x dash some matrix which is gradually changing x. So somehow this is a result for the general quadratic form. So somehow it's not clear. I mean, basically you say, well, this result here is yeah, well, somehow it belongs here. It's a general quadratic form, and the techniques for that, exponential inequality, central limit theorem, belong here. So somehow it's not in terms of this is all spectral methods. It's because Toeplitz formulation is the Toeplitz matrix is defined by the spectral density. It's the Fourier transform of the spectral density. This is the reason why spectral theory comes in and all over the place. And if you really want to understand this, you have to not to become an expert of spectral theory, but you have to learn a little bit to understand what it is about. Now, the point now is basically this assumption, which is so strange, this TV, these time-varying Cramea or the time-varying moving average assumption, is a general setup to discuss all these problems you want to discuss. For example, no one has done this in a proper way, in my opinion. If you want to just look at the covariances, I mean, you have a non-stationary process. Let's plot some covariances. Let's look whether they are time invariant. Would be a great idea at the beginning, and test for it. And no one has done it, in my opinion. So it would be still one open paper, or 2 or 3 whatsoever. And then you need a framework. I mean, what would be the framework? And actually, this would be one framework. This time-varying moving average would be one framework to investigate it. Now, bootstrap methods. If you say do a block bootstrap for locally stationary, non-stationary processes, right? I mean, resample the process in a one or the other way. You have to, and you want to investigate it. How do you do it? Again, you need and this is again, you need bubble 1. I mean, you need bubble 1 where you say we need a decent model for the investigation of our methods which we develop. Efficiency of estimates, misspecification of models, and so on. You can calculate the Fisher information, Lecam theory, Kullback-Leibler diversions, and so on. Here is a very prominent example. When you take the exact Gaussian MLE, then you can really write it up to a very, very, very small error. So think of root n convergence. So it really it's very strong approximation as this quadratic form with the pre-periodogram in it, or as the quadratic form here with the generalized Toeplitz matrices. Now it's important to say that there are other approaches. This thing, which with the time-varying moving average or the time-varying Cramea is now, I don't know, was the very first approach. It's an old approach. Now, other people have suggested new things. And for example, there is this predictive dependence measure by Wu. Zhu is here, I think, at least. I haven't seen him yet. Hi. So, Zhu and Wu used it, and Zhu used it in many papers. Which is an alternative to this here. It's a more modern framework somehow, right? It's a more modern framework. It's based on martingale arguments. It's a nonlinear framework, so you can study nonlinear process as well at the same time. So it's a more decent, more modern framework when you do things. But the rest is not touched by this. I would be very happy to see under the assumptions of these predictive dependence measure assumptions an exponential inequality for quadratic forms. I mean, you still need, if you start with a different framework, a different set of assumptions, it doesn't mean you are no longer interested in covariances, right? I mean, you still would plot covariances at the very beginning. So you have a quadratic form, you have still different problems. You want to plot a periodogram, plot a spectral density. You can investigate under this new set work of assumptions and see how you prove things there. But it does not it does not change these problems and that problems. It has the big advantage that in addition you can treat nonlinear problems with it, right? So you can in addition treat nonlinear problems in the same framework. Now there comes the next one, locally stationary approximation assumption by Michael Vogt. Michael Vogt has really done, has used this as a definition where you have this idea of that you can approximate your process on each segment by a stationary process. And basically this is very back to the origin, to the basic idea of locally stationarity, and he formalized this as a definition for a locally stationary process. So again, this is another framework, another set of assumptions which he uses for proving these things. And again, it would be nice to see an exponential inequality for quadratic form under that set of assumptions. I haven't seen it, we have discussed it, I have looked at it, tried to prove it, it's fairly difficult. By the way, proving this exponential inequality was the hardest research of my life. I really was sitting there for 5 years looking at this exponential inequality. So, okay. And now I want to really mention this one. This is the definition of locally stationary wavelet processes by Guy Nason, Rainer von Sachs, and Croissant in this paper 2000. And somehow this is somehow the counterpart in the wavelet world of this thing here. So basically I indicated you can estimate curves by wavelets, fine. That's not that difficult. I mean, if you spend some time and look at this and put some energy, you can solve the problem, right? But somehow the really merit of this paper, this is a breakthrough for wavelet processes, is really that you have now a framework to study many wavelet problems for stochastic process. And it's really that you wavelet is an idea for curves, right? And here it's really invoked in the process. The process itself becomes somehow inherits the local characteristics from these wavelets. So it's really a key paper because it is really built up the framework for the wavelet world. So somehow these definition of locally stationary wavelets is really in this point here, and it enabled all the research, and Guy Nason will tell us more about that. So perhaps I just stop here. I have 20 more slides, and it's a good point to end here. Thank you very much.
So Rainer, I think first of all it's a very impressive presentation. I liked it very much. My question is, do you think that local stationarity has made an impact on statistical practice? Is the world a better place because of local stationarity?
Well, this is a difficult question, and one answer to that is related to a personal fault, say on the side of mathematicians, in particular on my side, namely that I did not really wrote decent programs to all the methods. So somehow it's really the bridging is missing, in my opinion. So basically there are many new results, but when I tell an applied researcher about an exponential inequality, I mean, he may listen for 3 minutes, but then he is away and has his data problem at hand. So basically it's really, if I just talk about myself, it's really the failure of not providing easy to use programs on the computational side for practitioners. But and the second answer of that, and I know some of you have provided programs, so some of you are doing better than me, but it's really a little bit more challenge. So this is the typical story of the typical problem of mathematical statistics. If we want to really bring our ideas to the world, we have to bridge this a little bit and program it. But I think really that there are many new insights in that from coming from that. But it's our duty or our duty to really to build the bridge to the applied researchers.
Just an effort to answer this question a little bit in a specific way. The merit of having a mathematical theory about how to control deviation from stationarity might be in the fact that users know very much how to fine-tune estimation methods which work under the paradigm of stationarity. It's applied, let's say, in applied EEG, ECG Fourier analysis, many analysis. We have now fast programs that kind of fine-tune the parameters. Now, if we can offer, and that's one of the missions I think is behind this, we can offer a control how we can kind of transfer this experience to a locally stationary world, right? Where we try to very well approximate something, and we know about the degree of approximation, the precision, and where we can try to push our nice stationary method just a little bit further in order to give answers about, slow or abrupt change. Because the problem is a little bit, if you don't have a framework like what Rainer put up here on the left-hand side, you might end up in try and error, right? You might end up, okay, here's something which is, more general. So you try method number 1 and then method number 100, and then in the end you don't know exactly, is there a concept which method is more general or more efficient, and that could help to compare methods and to try to cook the complexity a little bit down. And that's what the user in the end needs. He needs to get a feeling, okay, I have this problem, I have as many data, I have as many information, I have this degree of uncertainty. So if I have a little bit of an idea what is probably more, working in this situation because somebody has an idea that this method, has this limits and the limitations, this method has this limitation, I believe that this can help. And that's why I see that it is important in order to tell people with 200 data, don't do this, maybe do this. If you have replicates, it might be better to do this and do this.
To give you one very concrete, simple example. Suppose we have this time-varying A01 problem, and we want to estimate the curve. And I think there are two possible solutions. One is really a local polynomial fit, if we believe that it's more or less a smooth object, or to apply wavelets if we believe it's more like a quickly changing object with different levels or so. And I think this is a message which applied people would not know, right? And I think just looking on segments and smoothing on segments is a not very good idea. And so I think we should provide applied people with these two alternatives, tell them what is the difference, when should we prefer local polynomial fit, when should we prefer a wavelet analysis, give them programs that they can try both, see what fits to their problem, and have some model selection criteria. And this is our duty, but I think we really have new insights which are important for those people.
So one thing, when we were writing, is Eric here by any chance? Molino? So when we were writing our book on nonlinear time series, the problem is how do you make this argument? And for stationarity, that's like modeling in the affirmative. If I tell you it's stationary, then you're set, you know what to do. But if I say, okay, it's not stationary, then that's modeling in the negative, right? So there are many different ways to be not stationary. But then, okay, so then you have to know, okay, so when writing the book, it's like, are there patterns? And the answer is yes. Like, even from finance, like explosions and earthquakes, you see data with similar kinds of patterns, right? So if you see something that's sort of noisy, then all of a sudden it changes and, you know, the amplitude is modulated, slows down, then you have a bunch of techniques for that. You know how to model that kind of thing. So you sort of take problems and you say, okay, if you see this is, you know, here are a bunch of models for why, you know, to explain this kind of phenomenon. And so you sort of group things like that, rather than just saying, okay, it's not stationary or it's locally stationary, and then how can that be? Well, you see patterns, right? There's certain patterns from different, you know, applications. So you could have an abrupt change, you know, where something changes, or you could have something like a screw's loose and, you know, something's changing slowly. So, you know, that's how you sort of apply that kind of stuff.
So did you have a comment?
Well, a question, maybe more a question to Rainer. Two questions. The first one is, I mean, well, I'm sure you didn't give us more details about these exponential inequalities, where you said this is a kind of key fundamental tool, which I fully
For quadratic statistics.
I fully understand.
For other problems, you need other exponential inequalities, by the way. Yep.
But my question is, well, I'm not familiar with these results. How sharp is it? Is exponential? Can you, for example, could you use it in order to tune parameters of your estimators in a finite sample world? I mean, did you try that to see how sharp they are? Because
I mean,
my issue is that already in much simpler models, asymptotics can be quite misleading. For example, at the beginning you showed these MSE asymptotics, and I think it's a quite misleading story how to do non-parametric statistics. To be frank, in much simpler models, even in independent error models.
I'm happy.
One should be very careful with it. So my question is,
I'm happy to learn about this more simpler things, but
but if you have
answer,
if you have a very sharp deviation inequality, then of course you could use it because it's a finite sample inequality, right? It's not so maybe you could try to use it in order to tune parameters for your estimates and so on.
I probably will not really make it. So basically, the idea is that you have something like the maximal inequality is something like phi, and then we have say x dash. I don't know. X dash, and then we have these generalized quadratic matrix is say some generalized triplets matrices of phi in the non-stationary case, and then basically it's larger than epsilon is exponential. Then eta is less than a constant, which we can specify exponential to the minus. And now comes business. I mean, I think the ideal world would be really the form of the Bernstein inequality. We are able to derive it without the maximal in the Gaussian case, which I think is the strongest result you can get. You cannot outperform it. So if you have chi-squared variables, for example, and then we are basically have something like minus eta squared, which is this is too much. We get in the general case a minus eta, and in some cases we only get the square root of eta.
And do you have control over the constant?
Yes. Yes.
On what does it depend in first order?
Okay, we have to discuss it, I guess. On the table. One thing is I'm a little bit proud of. We only need bounded variation of the curves. So we have our parameter curve. So when we say xt is a t over n xt minus 1 plus epsilon of t, I only need that this is of bounded variation. And the sigma is only of bounded variation, so we need no continuity at all. And maybe, this is a claim, and somehow these claims are always unfair. I think one could apply it to change point analysis because we make no assumptions about continuity or so at all. But okay, I'm very careful of that, and I know that really proving things is very often a work of, sometimes 5 years, and it's not that easy.
Okay, so I think that's a good place to draw the discussion to a conclusion for now. Just before we thank Rainer again, many people will be having lunch at Wolfson Court. If you don't know where Wolfson Court is, Paul has agreed to be our guide there, and we'll be meeting in reception in 2 minutes' time. But I'd like to thank Rainer in particular for giving such a great talk at the start of the show. Thank you very much.
Thank you.